Welcome, curious minds, to the deep dive. Today, we're plunging into some really groundbreaking new findings, stuff coming out from the James Webb Space Telescope. And it's really changing how we, distinguish between what might be a planet signal and just noise from its star. We're focusing on TRAPPIST-1, you've probably heard of it, that famous exoplanet host star, and specifically how its stellar flares, maybe surprisingly, are giving us a way to finally get a clearer picture of these distant worlds, and maybe, just maybe, their potential for life. So our mission today is to unpack how astronomers are cutting through all that stellar static, you could say, getting a better look at these planets. This new research, it really could redefine the search. Okay, so let's set the scene a bit. TRAPPIST-1, it's a pretty cool star, right? An M8 red dwarf, super well known because it has those 7 planets we know about, and several of them are orbiting right in the habitable zone. Seems like a prime spot to look.
It does, yeah. On paper, it's incredibly promising, a whole system packed around this small star. But that very star, TRAPPIST-1, and actually many active red dwarfs like it, they present a huge challenge.
Okay, what's the main issue?
Well, its surface is incredibly active, really dynamic. It's dominated by magnetic stuff. You've got star spots as the cooler, darker bits, and faculae, brighter, hotter regions.
Right, sort of like on our sun, but maybe more intense.
Potentially, yeah. And these features, they're not just, interesting surface details. They act as major noise. Contaminants. They really distort the light that astronomers need to collect, especially for studying atmospheres using transmission spectra.
That's when the planet passes in front of the star, right? And the starlight filters through its atmosphere.
Exactly. And imagine trying to measure a very faint chemical signature from that atmosphere when the light source itself is fluctuating wildly because of these spots and faculae. It's like trying to hear a whisper in a noisy room.
Okay, so that's the core problem then. How can we possibly tell if some faint signal, maybe a hint of biology, is actually coming from the planet, or if it's just a kind of fingerprint from the star itself fooling us, a sort of cosmic photobomb, as you put it?
Precisely. We've known for ages we need to account for this stellar contamination, but the big hurdle, the real difficulty, was that we didn't have direct measurements of the spectral fingerprints of these magnetic features, not for this type of star, until now.
Okay, so the breakthrough. Tell us about the solution. There was this research team led by Valery Vasilyev.
Yes, from the Max Planck Institute. They came up with a really clever approach.
What did they do?
They used JWST's 1’s instrument. It's incredibly good at picking up tiny changes in infrared light over time.
Time-resolved observations, you mean? Watching things as they happen.
Exactly. They basically stared at TRAPPIST-1 during 4 separate flare events, capturing data in unprecedented detail.
And what did they see initially?
Well, at first they noticed this persistent brightening in the star's light spectrum after the flares. And, initially it looked pretty much like a standard flare afterglow, something we expect to see as a flare cools down.
Okay, it's normal so far.
But when they looked closer, the data started telling a really different story, something quite unexpected. It wasn't just cooling. The analysis suggested the flares were actually removing dark magnetic features from the star's surface.
Removing them? How?
Through magnetic reconfiguration. Essentially, the flare's energy was powerful enough to rearrange the magnetic fields on the surface and make these darker, cooler regions vanish.
Wow. Okay, so the flares were actively changing the stellar surface we see. That's fascinating. The star's own fireworks are sort of cleaning up the view for us.
In a way, yes. It's like the flare happens and poof, a dark spot it was associated with disappears or shrinks significantly.
And these disappearing regions, you mentioned they were cooler, but only by a bit.
Yeah, just a few hundred kelvins cooler than the main stellar surface, the photosphere. But the key thing is, this research allowed them to be spectrally identified for the first time on an M8 dwarf like TRAPPIST-1. We could see their signature in the light.
And this connects to things we've seen on our own sun.
It does. We have seen magnetic structures on the sun disappear after flares thanks to high-res solar telescopes. We can physically see it happen, but measuring the spectrum of such a feature disappearing on a distant, tiny M-dwarf star, that's the real leap forward here.
So this makes you wonder, could this be common? Do flares on other active stars regularly sort of reshape their surfaces like this?
That's the big question this opens up. If this magnetic reshaping is typical, it really changes how we need to think about these stars and their activity.
So this is the first time we've actually measured the spectrum of one of these magnetic features on a star like TRAPPIST-1. Why is that such a game changer?
It's huge, because now that we have these specific spectral signatures, we know what the noise looks like in detail. Astronomers can subtract it.
Ah, so they can clean up the data from the planet.
Exactly. They can take the transmission spectrum, the light filtered through the planet's atmosphere, and digitally remove the contamination signature from the star itself with much, much greater accuracy.
Okay, I see.
And the direct impact is, well, profound. It means we can be much more confident in distinguishing a real atmospheric signal from the planet, from something that's just an illusion caused by the star spots or faculae.
Which gets us much closer to maybe finally detecting actual biosignatures around these red dwarfs.
Significantly closer. It removes one of the biggest ambiguities we've been wrestling with.
That really does sound critical.
Yeah.
Are there still challenges, though? Is this technique perfected, or are there limitations?
Oh, there are always refinements needed. Stellar surfaces are complex beasts. Understanding exactly how these features form, evolve, interact. There's still work to do on the models, but having this direct spectral data, it's an absolutely invaluable anchor point, a ground truth to build upon.
And thinking bigger picture, you mentioned active red dwarfs. These aren't rare, right?
Not at all. They're the most common type of star in the Milky Way, by far.
So that means there could be thousands, maybe tens of thousands, of planets in habitable zones around stars like this.
Potentially, yes. And this technique gets right at the heart of one of the biggest roadblocks to studying them properly, that stellar contamination issue.
It's like finally getting the right prescription for our cosmic glasses.
That's a good way to put it. And it makes you think, if flares can actively change the star's magnetic structure like this, what does that mean for the planets orbiting close by? How does it affect their environments, their atmospheres, their climate?
Could it mean some are actually more habitable than we thought? Once we strip away all that stellar interference confusing the picture?
It's possible. We might find clearer signs of atmospheres, maybe even water vapor, that were previously masked by the star's activity. The answers we find could genuinely redefine how we search for life out there.
It's really incredible. Just this one discovery, this new way of seeing, can ripple outwards and potentially reshape our whole understanding of these alien solar systems.
Absolutely. And it leaves you with a thought, doesn't it? Imagine what other kinds of noise, other confusing signals in our observations of the universe might actually hold hidden keys, hidden clues, if we just figure out how to look closely enough and in the right way.